Good day, everyone. Welcome to our talk on RISC-V, ushering in an open era of HPC. My name is John Davis, and I'm joined with John Leidel from Tactical Computing. And today we're going to tell you about what RISC-V is doing in HPC. We're going to start off with considering the question, can we create an open HPC system? And from that, we want to look at the history of HPC, starting off with the past, talk about where we are today, and then allude to where we can go to the future. With respect to that, we're going to talk about the special interest group for high performance computing as part of RISC-V that myself and John are a part of, and talk about the introduction software ecosystem, which is critical, and then move into how do we build an open HPC system with these ingredients that we talk about today. So historically, if we step back in time and go to the 50s, 60s, 70s, and look at software, they were dominated by closed and proprietary software systems, as well as hardware systems. And what these created, especially in HPC, were expensive, rigid systems that provided customer lock-in. They used custom APIs, and for changes, you had to pay for additional services. And that transformed in the 80s and 90s with horizontal platforms like Windows and Solaris, where you had a commodity horizontal platform that had standard APIs. There was still some lock-in for the operating system, for instance, but you had a lot more applications and resulting a lot more users. That was radically transformed by Linux and the open source software movement, where they changed the business model. They created the same standard APIs, but you had the ability for users to customize the solutions software, start from something that wasn't Scratch, and create this ubiquity. And so we're seeing this between everything from the IoT space to HPC. And that's very exciting. At the same time, we can look at the history just to get an idea of what that time span was. So the first release of Linux was in 1991. And shortly after that, we saw a flurry of large companies in the late 90s starting to adopt it. Likewise, in the late 90s and early 2000s, supercomputer centers like BSC were adopting it as the supercomputer OS. And then if you fast forward about 10 years later, by 2015, Linux was the de facto OS for everything from IoT, mobile, cloud to supercomputers. So today, if you consider building a software system that has a OS, Linux is probably your first choice. Now, on the hardware side, it's useful to go back about a decade ago and talk about Mont Blanc, which was a project started by BSC using, at that time, ARM processors from cell phones to build a high-performance computing stack. At the time, people thought it was ridiculous, but you can now see the kind of analogy between where ARM was at that point in time and where RISC-V is today. Now, we had a complete industrial software stack, applications from high-performance computing, system software, and ARM provided the hardware. Now, all the software stack components were malleable. You can change them, you could update them, and that was fantastic. So you could evolve that with hardware. Ideally, we'd like to be able to evolve the hardware too. And at that project scale and time frame, that was not possible. So we're really stuck in terms of the capabilities of the co-design of the hardware and software to make an optimal solution, but you can still demonstrate its utility. The result of that is seen today in Riken and the Fugaku system. So the Japanese took this idea, did co-design of the applications to architecture. By investigating select targeted applications, they could change architectural parameters like SIMD width, SIMD length, number of cores, those types of things to really adapt and design the hardware and software simultaneously. And that's a very powerful tool that then gives you an exact fit for the problem at hand. The result of that is the PostK A64FX processor. And it has components both of a modern mini-core CPU, as well as GPU-like performance and features, vector length, and so forth. And so the combination of those two resulted in a top 100 for the last 3 terms. So over the last 18 months, it's been the #1 supercomputer in the world, which is a pretty extraordinary feat. So in the span of a decade, we've gone from something that was relegated to only embedded or mobile type processors to the leading supercomputer architecture in the world. And so these are the types of things you can do when we start putting a community and doing all these components together. So if we summarize, today in the HPC stack, we can see from applications down to OS, a bunch of different work being done in HPC that is open source. And Europe has a lot of the leading components in that space. De facto OS is Linux. So all of the different supercomputing centers are running these over proprietary alternatives. And the entire landscape from cloud to IoT benefits from this open source ecosystem. It provides a common software platform, specification, and interface. And by leveraging existing components, we accelerate the time to build new functionality. So time to market, time to research are all accelerated by this, which is basically lowering the barrier to entry for other people to add these components. And fundamentally, whether a problem is small or large, you can crowdsource the solution. And so that's part of the benefit of open source. Now, unfortunately, when we get into the processors, the GPUs, and the ASICs, historically that's been closed. And so there wasn't the opportunity to build these components or build on top of existing components. So this inhibits the overall natural evolution of doing co-design, designing the hardware and the software together. So this barrier to innovation is something that we're trying to solve today. And as you'll see in later slides, something that we have to do. So why is this important? To get to exascale, we basically define an exaflop operating in about 20 megawatts of power. And this has some different physical and structural requirements in terms of building out buildings to house a supercomputer. What I'm showing here on this graph in the blue dots is reported by Top 500, the evolution of performance improvements over time. And as you see, every 4 years, we have a 10x improvement. Likewise, if we extrapolate that to energy per operation, it's the same thing. The actual energy per operation is decreasing by 10x every 4 years. And so at this point in time, to get to an exaflop, you have this very tight bound of 20 picojoules per flop. And when we just look at a single dual precision operation, that's about a 2 picojoules per flop, or equivalent to moving that 64 bits about 1 millimeter on the chip. So when we look at these solutions, we're really becoming power bound and power constrained. And so we need to create energy efficient solutions. So when we combine these together, we have this combination of open source software, which is ubiquitous, everything from IoT to HPC, and these new constraints, power on the hardware side, the lack of increasing in transistor density from the slowing or death of Moore's law, depending on your perspective. And these combine to create specialization from the hardware perspective. So we'll get better performance, lower power, improved cost efficiencies if we specialize. And at this point in time, before the advent of open source or ISAs, we only had access to software. So now we have the combination of both software and hardware to do the code design. So the advent of ISAs like RISC-V or Open Power give us that capability to create and build on a well-defined ISA that can allow us to build the hardware. In terms of momentum, we're seeing extreme momentum on the RISC-V side, and we're excited to push that forward. So when we talk about the open source ecosystem right now, as I mentioned before, just to illustrate, we talk about applications, GROMACS, NAMD, Quantum Espresso are examples of the applications which are open source that you can actually modify. Likewise, there are libraries and platforms, schedulers like Slurm, compiler tool chains, GCC, LLVM. All of these pieces are being put together to build up the overall system that then can be mapped to a RISC-V. And you can find a list of those RISC-V software components at the GitHub link below. Likewise, we're particularly interested in RISC-V high performance software and libraries. And John will go into more details in later slides on what we're doing there. But we also have a GitHub link that actually allows you to build the software for HPC. So why open source, right? And here's a quick summary of some of the key elements that make it useful. We want to have compatibility across implementations. So the software, even though it is open source, we want to be able to leverage it and make sure we have maintainability at that level. If you're using open source IP, the security is a big aspect. You can audit all of the IP. And as you look at the RTL or the different components, you can be sure from a safety perspective that there's no black boxes. And then the fundamental component of this, as we talked about specialization, for size, weight, power, area, customization, all those things are capabilities when we can change both the hardware and the software, and we can get exact feature match for the solution at hand. And because we have this flexibility to build from scratch or build from other existing components, we can get state-of-the-art implementations from a performance perspective using the latest technology nodes from TSMC or Global Foundries or Intel. Now, the nice thing about this open source ISA is the ecosystem enables us to have both small SME and large enterprise both provide solutions. So there's no vendor lock-in, and you have the capability to move as you want. Another exceptional aspect of this is sovereignty. There's freedom of access, and implementation of the design to production is guaranteed because of the open nature of this. And then the most fundamental part is this open collaboration. We can have communities work together to create faster time to market, leveraging existing IP, and faster time to research if you're on the research side. So the community is the big building block here. And that's one of the fantastic things about RISC-V. So when we look at this overall ecosystem, with the ISA at the middle, I have the software stack on the top, the RTL and the hardware development on the bottom, services on the right, as well as training and research and academia. That whole thing on the left gives us the ecosystem that we want to build and flourish for everything from IoT to HPC. Now, when we look at the membership, that community aspect is very important. We have over 2,200 RISC-V members and growing across 70 countries. Now there's a massive influx of chips to choose from, and you can look at the RISC-V website to see what's available, both open source and proprietary, things that you have to pay for. But we look at this and it is truly a community. There are over 1,900 individual members. And again, this is really building on that momentum. We also have several hundred companies. So the combination is really driving this ecosystem to produce more and more IP, more and more diversity. And our goal is to make sure that for HPC, we're not left on the side of the road, so to speak. So when we look at this, we can create a completely open source software hardware stack for the world of HPC. And RISC-V gives us that capability. It opens alternatives to the dominating proprietary solutions today. And we have complete technology independence using these foundational building blocks. And so fundamentally with RISC-V, we want to unify, focus, and build a new microelectronics organization industry around open source. And again, giving some of the components from applications GROMACS, hardware through OCP or Open Compute Platform, and accelerators, CPUs, and ASICs using the RISC-V ISA. So how do we do that? One of the ways we were thinking about this to organize was creating the special interest group on high performance computing. And so it has two main pieces. One is the vision. This is the technical and strategic imperatives that guide RISC-V to build this ecosystem to get us to the point where we can have this entirely open HPC ecosystem. And we do that by enabling new sets of software and hardware opportunities for HPC specifically. And that's everything from high performance at the edge to high performance in our supercomputers. And really, we want to be able to run both the legacy as well as emerging HPC workloads. And in that, I include AI, machine learning, and deep learning. Now, it's the full stack, right? We can't really ignore anything. So it's the traditional CPUs and accelerators that you think about, all the way up to enabling the software ecosystem and making sure we have alignment there with the ability to produce these, whether it's verification tools, foundry information, and really engaging with key industrial and academic partners to make that happen. So together we can all create this global technology independence using RISC-V and push the entire process forward, both from an implementation and an innovation perspective. Now, we have a bunch of different initiatives to guide and enable the community. And there's two things we need to do. First, we need to make sure that RISC-V is on par with existing technologies today. So in the virtual memory space, an example of that is the virtual address space that Intel just proposed for 57 bits. But we also have an opportunity to lead. So SV64, SV28, so 64 and 128-bit address spaces are an example of where we can set trends there. We need to make sure that from a ecosystem and roadmap perspective, we have an idea of what's happening and how to define that for high performance computing software and hardware. And that's a key driver to which things we do first. Obviously, accelerators and ISA extensions are part of that. And probably the most important thing that we're looking at first is a high performance software stack and looking at how do we enable RISC-V in that. So it's running libraries and applications in a RISC-V ecosystem. So with that, I'm going to turn it over to my partner in crime, John Leidel from Tactical Computing Labs, and he'll tell you a little bit about what the HPC software testbeds are doing today. John?
All right, thanks, John. So one of the interesting things that we decided to attack first in the special interest group for high performance computing is this ability to take a massive amount of traditional HPC software and actually use it for the internal gap analysis. So what we're effectively doing is we're taking this huge amount of mindshare behind HPC software and specifically the open source HPC software ecosystems and using it to determine where the gaps exist in the RISC-V ecosystem. So for example, we can start out with a set of tools such as XCAP for doing cluster management, Singularity and SPAC for package management, the various different programming model and compiler stacks. And on top of that, we can build sets of various different scientific solvers and numerical libraries such as Trilinos and FFTW. Then we can begin building benchmarks, LINPACK, HPCG, these various different things, and take that all the way into building full scientific applications. And the goal here is actually to use this sort of circular flow of software to determine what exactly we need to do from a microarchitectural perspective and a specifications perspective in the RISC-V ecosystem in order to really build a purpose-built RISC-V HPC device. So what we're actually doing is we're building this in an open source environment such that not only the people within the foundation, but the people outside the foundation can begin contributing and viewing the actual test results for this. So what we've built is what we call the HPC software test bed. So the RISC-V SIG HPC has set out a set of Jenkins build hosts that pull from GitHub a set of tests. Now, what these tests do is they actually build a series of compilers based upon GCC and LLVM, a whole myriad of different versions. And from those compilers, they actually start to build individual libraries, individual benchmarks, and eventually applications using those compilers to determine yes or no, are these pass fail, what gaps exist, what libraries don't exist, what things need to be ported, all the level of dirty details behind how we build this full stack ecosystem of RISC-V. And the goal here is not actually to look at the performance of the individual applications, but rather what we're trying to determine is what inherent gaps just exist in the software environment. So this is effectively what it looks like. We have a public Jenkins repository and Jenkins host that runs at risc5test.org. You don't need a login to go look at it. The entire public repository is open to anyone who wants to go check it out. Then we have a series of compiler tests. So for each different compiler variation, we actually have a full set of pipeline tests. So for example, in this view, we have things like the RISC-V GNU toolchain from the actual upstream master. We have the LLVM from the upstream master. Then we have a series of various different LLVM production compilers. So every time the tests actually get kicked off, all of the tests are run for each of the individual compiler variants. And what we actually seek to do in the future is take the individual compiler variants, then for each compiler variant, put in specific compiler flags to, for example, enable the atomic extension or enable the vector extension such that we can see where the individual software gaps exist based upon the RISC-V extensions that are present in the system. So the interesting thing about this is we do get pass-fail results that can be reported to the public, but what's also really interesting for other researchers and other organizations that are seeking to start developing RISC-V based software packages and eventually RISC-V based processors is you can actually go into the actual test logs and see exactly how we're building each of the individual tests. So one of the issues that we're dealing with from a foundation perspective is we don't have a whole lot of inherently Linux capable platforms that we can build all this software natively. So we do a lot of cross compilation. So what we have here is the ability to look at the individual logs and view the actual build rules required to do all the cross compilation for what are effectively very complex software applications and numerical solver libraries. So this is really, really key for us to be able to provide a service to the community such that everyone else can also participate and help us develop this software ecosystem. So as I said, the test harness is public. The actual test logs and all the test infrastructure is located at risc5test.org. The actual test harness itself is actually BSD licensed and it's located on GitHub at the link on the screen. The cool thing about locating this on GitHub and licensing this as a BSD license is anyone within the foundation or outside the foundation using our templates that we've provided in the repository can actually submit new tests. So rather than trying to submit tests to Jenkins and mess with the Jenkins scripts and all that level of difficulty, all you have to do is pull our test harness, which is effectively a set of shell scripts, implement your test in the shell script, and send us a pull request. And we can immediately start testing your HPC-centric software in the RISC-V ecosystem. So and the test harness handles all the directory structures, all the compiler paths, and all the necessary compiler flags. So all you have to do is worry about your specific test. So if anyone's interested in collaborating and sending us additional tests, please send us pull requests. So with that, using the initial development of the special interest group for high performance computing and this additional setup with the HPC software ecosystem, we really have the ability to develop customized hardware solutions for the HPC domain. We've made a tremendous amount of progress over the past 18 months in test harnesses and developing requirements and developing the gaps necessary to get a true HPC centric microarchitecture. The fantastic part of this is the HPC community has a long history in open source and has a long history in co-design. And what's further really interesting is the HPC community is very much ripe to be on the technology leading edge, both integrating traditional technologies from major producers as well as integrating some more bleeding edge technologies for things like specialized RISC-V extensions. So this open ISA really complements this ability to do open source hardware and open source software in a true co-design environment. So what we really feel is this RISC-V foundation and the RISC-V ecosystem really provides us the ability to accelerate innovation in both the research and industry. And we really hope this talk spurs additional research interest in the community such that we can continue this to continually grow. So with that, if you're interested in participating with John and I and the remainder of the special interest group on high performance computing, the meetings are open. The mailing lists are open. Please send us a subscription request on the SIG HPC mailing list. And with that, I'll turn it back to you, John, for some closing words.
Thank you very much, everyone. Like I said, and as John mentioned, we look at this perfect marriage of innovation in HPC being fueled by innovation in RISC-V, and that combination with open source software gives us the ability to create an entirely open ecosystem. So we see RISC-V ushering in an open era of HPC using both the open source software community as well as this open source hardware community. Thank you very much.
Thanks.